Right. I finally figured out how to get my new coach, and this is my first LHD bit. And please help me out if if I don't do something right. So I'm gonna be leading this session on IoT 101. So we're gonna do some drill, and we're gonna upon it in the next two sessions and culminate in a proper project. All right. So give me 1 second while I share my screen. Okay, give me. All right. Is the lag gone now? I'm just trying to figure out if it is. Right. If there's still a lag, I think there is. So what I'm gonna do is I'm gonna rejoin. I'll see you back in 5 minutes. All right. I think the lag should have gone now. Can you guys please confirm? Awesome. Awesome. Finally. Great. So let's start over. I'm so sorry for the glitch. I'm still figuring out StreamYard. So great. Let's get started. We're gonna have a nice icebreaker and we're gonna have a couple of polls. So let me first walk you through the PPT. Okay. Great. I can see all of you are really happy about the lag being gone. So am I. I am static at this point for there not being a lag. So what I had to do was I had to switch my device, the one that I was joining from. So I'll have to open my PPT here again, which shouldn't be a problem for another minute. So great. Great, great, great. This one. So I see a couple of questions. By the time my PPT opens, I'm going to answer some of those questions. All right. So some of you are asking about swag. There is a process of registration and check-in for which you'll get a swag. Let me see. After I get my PPT up and running, I can show it to you by sharing my screen. Okay. So I'm gonna share my screen. All right. Let me know if you guys can see my screen. Right. Alrighty. So what you want to do is, if you want to get swag, is you go to hackp.ac. So once you go to this page, you can register, and once you register, you can fill these forms. So you've got, if you fill the week-long form, you've got access to the first tier of swag, and then if you check in every day, you're gonna get a different kind of swag. So let's just look at the form, and And that's right, Scarlet69 is correct. If you just fill out the forms, you're eligible for swag. We just, we really want to encourage you and appreciate you for showing up. So it's okay if you don't follow, complete the challenges. It's okay if you're just here to listen, learn, ask questions. If you already know the topic, we welcome you to come and contribute to the discussion. All right. So great. So you can let me show you. All right, so I think we've covered the process of check-in. In case you guys still want to uh, register and do not have the right slide, I am putting the right link to it in the comment section, so you should be able to see it there. There you go. I've put the link in the chat box. And I'm just going to stop my camera because my computer is really lagging because of it. So give me 1 second while I share my slides. I'm again very sorry about this. Alrighty, IoT session 1. Okay, so today we're going to be walking through the basics of IoT, and we're going to be covering a lot of theory today because the next two sessions are going to be super hands-on, and there are a lot of terms that I want you guys to be acquainted with. So if there's anything today that I say, sure, I'll be sharing the PPT with you guys soon. So I'm going to be sharing a GitHub link in which everything we do is going to be uploaded in front of you live. So let's say, we're going to be working with devices. Now, I understand not every one of you has access to those devices, the microcontroller, the sensors that we'll be using. So I'll of course show you, demo it to you on the real sensors and the microcontroller, but we'll also be writing scripts to, demonstrate the behavior of a microcontroller or a sensor, and we'll understand what are the different kinds of sensors and how to choose a microcontroller. And there are tons of concepts that we're going to cover, but before we go on to the hands-on part, I want to make sure that you guys are on the same page as me when it comes to the terms, the technical terms, the slang even of IoT that lots of people use. We're also going to cover the difference between IoT and IIoT. How do you really define a product as IoT and IoT? and the parameters that go into selecting a device, right? So if you pick up a wearable watch that drains out in 5 minutes, it's really quite useless, right? So how do you decide, how do manufacturers and designers really choose the chipsets that go into it? What are the different types of chipsets available? What are the protocols available? So we're going to do all of that, right? So let's move on. Intros and icebreakers. So before I introduce myself, let's do a quick icebreaker. So I want you to, whatever the first thing that comes into your head when you hear the word IoT. So when I hear IoT, I can see like a mesh of cloud network that comes to my head. uh, so you put in the chat whatever comes to your head, right? The first thing that comes into your head when you hear the word IoT, and if you have a cool story about how you heard it. Okay, Cant guy says cloud. Awesome. That's as accurate as one gets. Alexa, great job. Madhuri, please apologize if I'm you know uh, pronouncing something wrong. Google Home, automation, Arduino, tiny devices. Great job, you guys. You guys have a really good idea about what's IoT, which is awesome, which is perfect, which is exactly what we're looking for. Uh, IEEE, Tesla. Interesting thing to think about when you're thinking of IoT. I saw a Fitband somewhere. Smart classrooms, great example of IoT. Connected devices, perfect. That's exactly what I want to hear. Fitband, awesome. Sakshi, great job, you guys. Agribots, another very nice answer. But let's dive into how if Agribots would really qualify as an IoT device. Ice, iPhone, all right, nice. Monitoring systems, awesome. All right, you guys. You guys really have a very good idea as to what is IoT. I had a couple of polls created, but now they're on the other system because I had to switch systems because of StreamYard. So we're going to cover the polls in the next session, I guess. But today I think we're going. Great. There's a question about fuel economy systems in automobiles. I'm sorry, I don't think I'm qualified to answer that question. So let's move on, right? Who am I? I'm a very new coach at MLH. I think a couple of you might have met me or interacted with me during a couple of hackathons in December. And yeah, I am super excited to be here. I'm super pumped. MLH is one of my favorite communities that I like to interact with. I've been following them ever since they came into APAC. And it is such an honor to be here, talking to you wonderful community members, because I can bet the things that you guys are doing, you guys are already pretty great at it. All right, so I identify as a maker. I love to do craftsy things. I love mixing things up. I have a pretty strong background in IoT and embedded systems. I've worked with a lot of devices. I've worked with different types of businesses, in IoT. And I'm a hackanista. That's how I identify as well. I love hacking. I participate in a lot of hackathons. And if you ever want to connect with me, you can connect with me on the following streams. All right. Great. All right. So there are a couple of questions that I will take up again later. So do remind me with those questions later. Okay, session one. This is the first session of the three sessions that I'll be conducting. So, like I've mentioned earlier, today is a very light session. We're going to talk about IoT. I welcome you guys to, throw questions. Some really great answers we've already got. You guys are on the right track of IoT. You identified most of the devices that, qualify for an IoT device. And I think it's going to be a fun session with you guys, giving me some nice challenging questions, and making me think too. All right, so intros and icebreakers, we're through with that. I of course ended up wasting a lot of your time because of the StreamYard thing. Again, apologies. So we're gonna end it. We're gonna keep it short and end it soon. So if you have questions, definitely keep throwing them. All right, session 2 plus 3. So you mentioned a lot of things, and like I said, we're going to be covering a lot of uh, hands-on stuff in the next sessions. if you guys already know what we're doing today, definitely stay back, help me answer questions. I would really appreciate that. And if you guys are new, definitely throw more questions. We're up for debates, even if things get a little opinionated, right? Awesome. So by the end of the 3 sessions, these are the things that you would have learned. What's an RTOS? How do you get connected to a cloud? What are the different sensor signals? How do you identify sensors? Industrial solutions. How do you define industrial solutions from a normal product idea that can be retailed? And you would have deployed an IoT project. It would be an end-to-end solution with data going to the cloud and you receiving data from the cloud. Oh, all right, great. So what is IoT? Now, here is a time to get in the comment section and start commenting about what's IoT. Thank you, Madhuri. That's very comforting. Internet of Things. That is perfect. That's a great answer. I'll share the check-in link again in a while. Great job, you guys. Internet of Things. And great. So you guys all are acquainted with the full form of IoT, which is great. I am seeing a really nice answer that says sensors that connect to the cloud and work on actuators, which is great, which is a great answer. Another great answer, an interconnected network of devices. No, Amit, you haven't missed anything. We're just starting off connecting hardware to sensors. Wow, that's a very beautiful answer. And this is perfect. Thank you, Shivadeep. You just made my life so much easier. The basic definition of IoT is human independent communication, which means that machines being able to talk to each other without human intervention is IoT. Now, okay, I'm seeing still some great answers and keep them coming. I would love to know what you think, definitely, right? But so basically what IoT is human independent communication, which means your devices being able to communicate, take decisions all on their own without you having to interfere. Now it uses ML and AI. Of course, IoT is an integration of multiple technologies. You can use literally anything with IoT, from AR VR triggering IoT, voice assistants, games. You can just think about it and you can probably integrate it with IoT, right? So human independent communication, that seems too vague, right? I mean, how do you differentiate between an IoT device and an M2m device, like a machine to machine? I mean, my sensor connecting with my Arduino is also communication without me actually interfering. Isn't that IoT? Well, no, not exactly, right? Why? Because IoT is specifically using the internet. Now, the internet does not refer to the data network per se. It can mean anything that connects devices wirelessly and allows them decision making without actually, using any wired interfaces. So, your mobile phone, one of the best examples of IoT devices, right? So this is nice. So Pikes mentions involvement of the cloud. When we now look ahead at different types of solutions, we'll realize involvement of the cloud is not necessary per se for it to be an IoT device. Yes, there needs to be a connection, a wireless connection, and independent decision making, but cloud not exactly. To hint you on, what I'm referring to is edge devices, right? Edge devices, literally their job is to take decisions without actually having to refer to the cloud and the database that they're connected. No, IoT is definitely not hard for beginners. Like I said, IoT is an amalgamation of multiple technologies, hardware, software, programming, and the how you choose to really interface your devices is completely up to you. So you can decide the tech stack that you use. How do you use the tech stack though? We'll look into that in a bit. All right. So let's move on. Components of IoT. Okay. One of you mentioned, sensors connected to a device and actuators. That's perfect. That's exactly what we mean when we say components of IoT. And I see a lot of people who say they're new to IoT, which is perfect. Another great question here is prerequisites for learning IoT. No, this session is exactly for you to make you understand what goes into making an IoT system, and we'll be learning all the components together, from how do you identify sensors to, well, all the components of IoT that we'll look into right now. Awesome, great. So we're already we've picked up nice pace, so I'm happy about that. Great. So these are the components of IoT. So when you ask, are there any prerequisites for IoT? These are the prerequisites for IoT. You need to understand all these components. You need to be able to interact with all these components, set them up, and then connect them, and then set up their communication. Right? So, great question. We are going to build a project, and by the end you're going to have an entire setup which runs on Azure cloud. So another great question, where to buy hardware. I will be sharing links to the devices that I bought from, where I bought from, but you do not need devices for this session. I'll be showing you real-time demos from the devices that I have, but we'll be writing scripts to emulate the behavior of a sensor. In the process of that, we'll also learn the kind of data that a sensor deals with, and what the kind of sensor data that we get on a controller, and how we really process, how the controller really handles the data, right? Yes, I'll be sharing a GitHub link in which I'll be uploading everything as we do in the session. Again, today is a theoretical session, so today it's limited to these slides, and I'll be sharing these slides. There are some great speaker notes too. Once you get access to the slides, there's a lot of info there that you'll find. All right, so looking at the slide that we have in front of us, right? So we can see that there is a device hardware, there is device software, there's communications, there's cloud platform, and then there's cloud applications. That is precisely the entire IoT network. So for an IoT, Internet of Things, you need internet, you need things, and you need them to interact over the internet, right? So first is a device hardware, which is basically your microcontroller or your processor or whatever, that your basic device. And it can be as something as small as a sensor, but you're going to need some other hardware to kind of peripheral it to the sensor. So that's your basic device, right? That's your first device, the first thing in your network. Then there is the device software, which in this case can be your RTOS that you're running, and also the UI that you're interacting with the trigger. This In this case, the device hardware does not always have to be a sensor. It can be voice triggered, it can be your Google Assistant or your Alexa, right? So all of these things are your first thing, right? The first thing that starts the entire chain of events, right? And then there's your software, which is an interaction. Like I mentioned, it can be a UI, it can be a button, it can be the RTOS running, which is scheduled to talk to another machine. All right. And then there's communication. That is, after getting the trigger, the system starts. So it's going to start communicating. So for a simple example, the most simple example I can give you is you triggering a light bulb with your assistant. All right. So your assistant, when you're asking them to turn the light on, what they're essentially doing is, once you trigger, so that's your first your user interface, that is your voice. So as soon as you tell them turn the light on, they're going to first search for the light labeled unique device identifier, which was very accurately mentioned by the definition that I displayed on the screen. And that identifier is now going to communicate with the bulb, which again is connected to the internet. So in our case, it can be using Wi-Fi, it can be using XB, it can be using Bluetooth. These are all different networks and different internets available for your devices to communicate. Fair enough. So that's your communication part, right? Then there's the cloud platform. So your voice assistant first connected to its cloud, right, where it has access to the devices that are connected, which has access to what device is currently turned on, is accessible, right? So that was their first communication. Then once they identify it in the cloud that was the first communication, that your voice assistant accessed the cloud. Then once your cloud assistant once the cloud connected, it communicated which light to be turned on, right? So that was another part of the cloud platform communication. This is not necessary if it's an edge powered device, right? And then the cloud applications handle was turned on, turned off, whether it got an acknowledgement. All right. To simplify this example, let's come to the next diagram, right? You have an input, you have a sensor. Again, the input you can see can be anything. It can be voice, it can be sensor, it can be a threshold data of a sensor. Then it goes into computing, that is your processor. The processor will first extract data. It will check whether the threshold for triggering is matching. It will send over the internet. And then once the internet, you know, verifies, if you have a database running, if you're checking it against the data, it will pass it on to the actuator. These actuator in your input sensors, they're not connected, physically. They're connected via the internet. I honestly hope you guys got the concept. Now I'm looking at the questions. So if you have any questions regarding what I explained, go ahead and bring them on. So what project, you're going to basically write a script in which you're going to emulate a sensor behavior. You're going to send that to the cloud, and on the cloud, assuming you're getting data from the sensor, you're going to send off more data. Let's say you want to turn on a motor, to another script which will verify whether your data is coming or not. What is an actuator? That is a beautiful question. See, like I said, these terms we'll be using again and again, and I'm glad you guys are asking. So an actuator is anything that converts your electrical signals into movement or into actuation, right? So for example, in a pneumatic device, your piston is the actuator, right? And your relay is the electrical signal that is going on to the piston. Or your motor, right? If you're actuating circular movement by a motor driver, that is your entire actuation circuit. Does that make sense? Another great question. You do not need to install a lot of software. We'll be running Python scripts. When we do start running Python scripts, we'll be installing some Python packages, but that's pretty much it. We will be using Azure, so I do suggest you check out the GitHub developer pack and sign up for your student Azure package. I'll be walking you through these steps by the end of the session. We're not going to be using emulators per se. We're going to use Python scripts to emulate the behavior of the sensor. How do you emulate the behavior of the sensor? By sending in data. We'll basically send data to cloud. Well, yes, a little bit, but you don't have to worry about it, because we also have parallel sessions going on Python taken by Will. So do join them. He's covering everything from the basics, and you should be good to go for the sessions. We'll be using very basic Python. You can link your personal email, but no, you will need one college ID for verification. So I think they have a system of verification through when you send a photo of GitHub, your college ID to. You'll have to check that. I'll probably check and get back to you if I can, before someone else probably answers the questions. Yep, controlling lights through mobile software is an example of IoT, because you do not just control it via cloud. You actually control it using either Wi-Fi, Bluetooth, XB, or or one of these protocols or networks. From next session, we'll be using Azure. Today, I'll show you the setup, what you need to be aware of, the terms you need to be aware of, and some documentation that I would like you guys to go through, but it's completely optional. All right. I'll take more questions regarding the signing up in the end of the session. Are there any questions regarding the components of IoT? Sensors, UI, user interface, the trigger of the entire system, communication, which is basically your network. Again, Wi-Fi, Bluetooth, Zigbee. All of these are examples of networks and protocols that suffice for communication. Then there's the cloud platform. In our case, it's going to be Azure. If you don't want to run Azure, there are multiple other clouds. I won't be able to show all of them, but let's say if you want some mentoring there, you can always reach out to our mentors on Discord, and I'm on Discord as well. Then there is the cloud application, which is basically taking the data verifying it in the cloud, and then deciding what to do with that data and sending it on to the next device. And the same thing happens, the same cycle of triggering happens on the other side. No, you do not need hardware for this session. Of course, it will be great if you guys can get your hands on some later to actually deploy solutions, but no, it's not necessary. All right, great. So I just realized that banner had been up for a bit. I completely forgot to take it down. Great. Beautiful question. Security is a very, very important part of IoT, and we'll just cover it in a bit. Uh, yeah, we'll be using C and Python. C because I want you guys to get acquainted to the real RTOSs out there. You guys don't have to use that. If you guys have hardware, I'll be uploading code files and you guys can try that later on. But we'll keep it simple, short, and really, really approachable in the session. All right. No, we won't be using Arduino IDE if that was your question, Silicon Bug. We won't be using Arduino IDE. We'll be using Python scripts. We'll be using the cloud. Yes, ML and AI is very actively integrated with IoT. Check out EdgeML if you guys want to know more. I won't be covering that in the sessions, but I'll be giving you links to resources in the end. You will get the recordings later, so in case you're jumping midway, do cover up there. All right, great. So I'll move on. I'm going to assume since there were no questions regarding the components of IoT, you guys have got a pretty good hang of it. This is very, very important, the IoT architecture, because when we'll be writing scripts and when we'll be actually implementing the entire, stack, you need to understand the IoT architecture, right? So first is the collaboration and processes, or the user interface, that is your trigger. If you see, it's in the reverse order, and of course the first and the last things can always, so it's IoT is basically a circular loop if you think about it, right? One thing triggers the other, then there's an acknowledgement message, there's almost always an acknowledgement message. All right, so let's start from the bottom, right? So your first is physical devices and controllers and your UI. So they're both triggering your entire system. So it can start on either of the ways, right? You can manually trigger the entire process using your entire process setup, and then there is the physical device, which is of course automated and is running probably an RTOS, which is scheduled to do certain tasks as per priority, right? Then there's connectivity, right? Connectivity is basically, again, cannot say this enough, right? Wi-Fi, Bluetooth, Zigbee, they're all examples of connectivity, right? So taking the data, doing some amount of processing, sending that process data. So in case, let me give you an example. I understand if lots of terms are new, go ahead and ask them in the comments. I'll definitely clarify. Okay, let's say you're taking an accelerometer, right? Now the accelerometer, when you're connecting it to your microcontroller, right, which is basically your device on the internet, accelerometer is not on the internet, right? So you're never going to take an accelerometer and just get the values. You're going to connect it to a microcontroller, which is your thing on the internet. All right, now the accelerometer values that the device gets, you can't just send it to the cloud. If you ever look up an accelerometer library, there is a lot of register level programming that happens. All right, and we're getting these raw values. These are 5-digit values, very sensitive values, and you can now, based on how you process these values, you will get certain results, right? So in case of an accelerometer, we usually, if you ever go through a library, which I completely insist that you do, right? uh, a very good example of a really nice library is MPU6050. I think Adafruit or SparkFun, one of them has a really good library, and if you go through it, you'll understand what's happening. Your register, what we do is, from the device we read the register of the accelerometer, right? And that accelerometer register has a random value. I mean, it's not a random value, but it's a value that is not really of any use until you really process it, right? So once you process that value, right, in some cases dividing by gravity, then there are different values, and there's a beautiful data sheet of it as well, right? So once you process that value that is either telling you the tilt of the device or the gravity or its level. That is useful information. So there's some level of processing happening on the device, right? Which is basically edge computing. That is the third component, right? Connectivity is first you're getting connected to the cloud via some protocol, right? And this protocol has to be a wireless protocol. The third one is edge compute, which is basically processing the raw data. Sending data straight away is more or less useless in most cases, especially the better the sensor, the more complicated value you're getting, and the more processing you can do on that value, right? So that raw data first gets processed into a more useful data, right? That data is now sent over the cloud, which is then leads to data accumulation, right? So now you've tons of data coming in. You can see graphs being created on your cloud dashboard. Now this data, right, the data that you've received on the dashboard, which is a little processed and can be worked upon more, is going to be abstracted, right? Now you'll apply different algorithms. This data you'll either make models out of it in case you're trying to use ML of some sort, in case whatever happens to this data, right? Which is called data abstraction, aggregation, and access, right? Then there's the application. After you've done, uh, collecting the data, analyzing it, taking out the bits and pieces, and really breaking it down, you can now use it for application. You can now take out analytics and decide what to do with this data. In which case, one of the simplest examples is pushing a notifications, right? Let's say you get some amount of data, you get one particular data, and you push a notification. That's the simplest way to understand IoT architecture. Now, I'm going to look at the questions if you have any now. So if you do and have any questions, definitely pop them up. Thank you, Shivadeep. That's really, really flattering. Absolutely. So this is exploring IoT from the very start, right? So now in the next slides, we look at the different options available, which is tons, right? In terms of devices, in terms of networking protocols, in terms of network. So sure. So edge computing layer is basically, see, it says data element analysis and transformation. So like I said, right? Edge computing over here does not refer to the edge computing that you learn in the MLAI class, which is basically running some kind of a ML model on the edge without actually referring to the cloud, right? This edge computing over here means processing the data at its very start. Like I mentioned, when you're using an accelerometer, what the algorithm is doing is it goes into the register of the accelerometer module and reads it. And that value is usually a 5-digit, 6-digit value that means nothing to the cloud. I mean, if you push it over cloud, even taking out patterns out of it is going to be difficult. So what you do is then you process it. So let's say I know that the sensitivity of it will vary when I divide it by so and so value of gravity. The gyroscope value will be so and so when I divide it by so and so value. This basic processing happens inside the microcontroller without really referring to any cloud, without referring or sending the data anywhere. Basically, this is the edge computing. Did that make sense? Esja 2001. Did this make sense, Darshan? The coder, the edge computing part. Thank you, Soham. Thank you so much. Very, very flattering again. Awesome, you guys. Great. So let's move on. Are there any questions regarding the architecture, though? So in data abstraction, what happens is all the data that you collected, let's say I've got accelerometer data telling me that I've got a graph saying it went 2 meters up, 3 meters down, 4 meters up, 5 meters. And that is the data abstraction, right? So that is the data accumulation, right? I've got a graph of the different data that I've received. Now, the data abstraction is my algorithm telling that at 5 meters, you need to do something else. That is data abstraction, basically working with the data. Again, this is a very simple example. You can do so much with this data, right? What you can do is you can take this data, put it into an AI ML model, and then actuate it with complicated data. But in case of an accelerometer, you want to send a notification at 5 meters. So data abstraction, what will do, it will wait for the data, it will keep analyzing the data, and every time it goes over 5 meters, it's going to send a notification, right? And then the last part comes collaboration and processes. Once you've got the notification, that's again you interacting with the entire system, and you can trigger the system in a reverse way. Data enrichment, did you mean abstraction by any chance, Cypher Wizard 9? Sure. So let's cover this. Let's give an example to cover this architecture. Like I said, let's take an accelerometer. So let's say you have a wearable device, right, which only has an accelerometer and a device that connects to the cloud. Okay. This device is going to notify the parent if the child climbs too high. Let's say one slide you haven't allowed the child to climb, and then it's supposed to notify the parents if the child is there, right? So what's the first thing? That's the physical device and controllers, right? So that's your device and your accelerometer. Next is connectivity. How is the device sending all this data to the cloud, which in our case can be Wi-Fi, Bluetooth. uh, think about it. When you think about it, if you want the child to be away and the parent is not nearby, it's going to have to be some long distance communication. So let's go for Wi-Fi right now, right? So let's say you've got Wi-Fi, you've got some kind of protocol running. Again, I'm throwing off this word, we'll cover it properly. Let's say it's running MQTT, right? We'll cover what's MQTT in much more detail in the next session, I promise, right? It's a protocol, a low power protocol, and it's running that. All right, so that's connectivity, that's your connectivity layer. All right, then there's edge computing, the accelerometer data being processed into your device. The device is going to get data from accelerometer, and it's going to do some kind of analysis and processing there. That's your edge computing part, right? Which is not basically referring to any kind of periphery or any kind of network to get that data. Then is data accumulation. It's basically sending all the accelerometer, process accelerometer data to your cloud, right? Once it reaches the cloud, then there's abstraction. Basically, you're going to uh, aggregate and access it, right? What kind of data do you want the user to actually know, right? Then that's application, right? At 5 meters, when you know the child's gone up 5 meters, you want to send a notification, which is collaboration and processes, which is basically people getting involved in notifying, and that's where the human part comes in. Did that make sense? Absolutely, Darshil. So Darshil mentioned that data abstraction is when you hide the irrelevant data from the user. So when you see, so of course, when you're working and at 5 meters, when you're sending the notification to the user, you're only showing and you're only telling the user about the 5 meter data. Do we prompt the user later on regarding the data? Yeah, so the data that is accumulated, that accumulated data also has the user has access to it depending on the application, right? I mean, if it's some kind of an IoT application, it really doesn't matter. There is a very nice question here. Quite honestly, I can't answer this. I'm not sure. So yeah, basically any processing that you're doing at the ground level without connecting to the cloud is edge computing. All the processing, all the data verification that you're doing in the device, in the microcontroller, without using any aid of the cloud is basically data edge computing. So I'm going to say yes to that, but I'll definitely get back to you about this particular question in the next session. After the edge computing, we always send data to the cloud after the edge computing, right? Because if you send the raw accelerometer value, it's useless. If you're going to run the entire thing on the cloud, you can do that, you can definitely do that, you can send it completely and then do everything there, but it's really you taking up a lot of bandwidth, because remember, you're sending a 6-digit data. In this case, you can process it and very easily bring it to a 2-digit, 3-digit data, and of course you'll also save on the bandwidth. Does that make sense? Surya, no, there is no challenge related to IoT that I'm aware of. But if you look at the form, in the check-in form, you will know what all challenges are there today. Automatically, yes, in the sense that your algorithm running will send the data to the cloud, right? I mean, it won't automatically. You'll have to program it to send it in some manner to the device, to the cloud. Sure, it's basically after your IoT system has worked, right? Your entire IoT system, the final process where the collaboration and processing. So, what you got the sensor data, you accumulated it, you processed it, you sent a notification. What next, right? So, what happens to the notification? What the application does with the notification? Does it show some kind of map there as well? Can you share that data? How is that data being used by your business, by by the parents in our case? Is all examples of uh, collaboration and processes. Sure, let me send you the link to check in right now. All right. uh Great. Any questions regarding architecture now? Yes, Darshil, the edge computing is done on the device. Okay, so I'm going to move on to the next slides. If you do have any questions regarding the architecture or you want to talk about it again, you can reach out to me on Discord or any of the channels that I've mentioned earlier. All right? All right. IoT and IIoT. Okay, I'm going to go through this a little fast because we're slightly short on time. Right? I'm going to try and cover this in 20 minutes because there's a really nice session right after this session, I think exactly in an hour. So I'm going to try and keep it short and sweet. And if you have any questions, definitely put it in the comment section. In case I end up looking over them, reach out to me. I am happy to clarify, right? IoT is something I absolutely love and happy to indulge in a conversation anytime. All right. So how do you differentiate IoT from IIoT? Okay. So we went through the architecture, right? How what are the features that every layer that has to have extra for it to become an industrial solution? So IIoT, what does IIoT mean? It's industrial internet of things. It's basically really large scale applications or applications that have high stakes but low risk, right? Or if it's high risk, it's low stakes, but they're used for really huge applications, basically, in terms of the number of devices, in terms of the amount of data collected. So that's what's IoT. So now if you look at the slide carefully, right, you can see that there are two more edges with features, right? There is cross-cutting functions, then there's system properties, right? So each layer in this first architecture layer that we went through, right, the physical network processing storage and the abstraction layer, right, these these layers have to have some certain extra features for them to really qualify to be IIoT, right? So then there is security, safety, privacy for it to be a cross-cutting functions. For it to the system properties for them to qualify as IIoT, there's intelligence, availability, dependability, scalability, and of course interoperability. So too many big terms, right? I mean, what do you mean? Like, what really means by IoT? It basically means that if you're going to deploy something on such a large scale, right? And again, large scale can be a huge machine, it can be a really big number of devices connected, it can be really sensitive data that you're accessing. If it's an industrial application, that means the stakes are either high or the risk is very high. One of the two, right? It means that the data should be accurate. The data should be confident, protected from any kind of violation or any kind of, capturing. It means that the network should be super stable. And if, of course, you can't promise the network, the data being sent should be sent in somehow that it's always accurate. Imagine running a very sensitive health device and the device just dies and starts sending random data. It can really screw up the results, right? So let's say your device will die at some point, right? You need to be what would an IoT solution do? It would have a very nice death message that, hey, now whatever data comes after this is probably going to be random. I'm not sending it from the sensor, right? So accurate, very sensitive information should not be violated. And so these are some basic things that make IoT. Now then comes, of course, the cross-cutting functions, or the system properties, right? How much better an algorithm can you run on it? uh, is there a lot of processing happening on the edge of the, that is, are you processing a lot of data on the computer, on the device, before you're sending it to the cloud? In which case, if the device is malfunctioning, there could be lots of wrong processing data that's sent, right? So these are some things that I makes IoT and IoT device. um so IoT should have a bank locker kind of security, but better than a bank locker. See, that's the thing. Not every time security is what you're looking for in an IoT device, right? When you say industry, there are tons of industries. It depends on the industry what you're prioritizing. Okay, I'm going to skip one of the comments and move ahead. So these are some of the things that make IoT and IIoT differentiate, right? So on the left there is IoT, and on the right there is IIoT, right? So IoT is commercial and consumer convenience. Your light bulb, right? That's my favorite example of an IoT device. Okay, so it turns on when you ask it to the first time. It doesn't, you really don't care, you'll just say the command again, right? Of course, if it's a good product, it will turn on and it will be very accurate, but if it doesn't, it's really not affecting anyone, right? But for an IoT device, if your things aren't perfect, they can really damage. So how do you know it's an IoT device? When it's being used for something that has high stakes, like monitoring and managing systems in industries like defense, manufacturing, healthcare, and others. Again, see, these industries are so diverse that it is possible that you know uh, some features take priority over the others. And of course, any optimized solution, if it's a very nicely optimized solution, it will never qualify for an industrial device, right? Because you need some things on a very priority feature basis, and you can always compromise on some of the others, right? Focus development, smart devices, you want things to be able to communicate with each other, maybe not thoroughly but a little bit. These are sophisticated machines, right? For example, a health device, you're processing some very high, you're processing some very sensitive and high amount of data, right? When you're making a health device, right? Degree of applications, so like I said, sensitive sensors, advanced controls and analytics. Your light bulb, right? Or you configuring your light bulb to turn on through a certain sensor, like a heat sensor or a temperature sensor. Low risk, barely any stakes. Look smart. You can completely. It's ease of convenience, right? It makes your life convenient. Degree of application in a this IIoT would be simple application with low risk impacts. Again, it's a combination. If it's low risk, it's going to be high stakes. If it's low stakes, then it's going to be high risk. Again, healthcare devices are a great example for that. Okay, there's a great question here. I'm going to take that once. So, would a store scanner count as IoT? No, it won't. Because first of all, the store scanner, if it's not sending the data over the internet, and if you're just scanning the barcode and it's sending it via the wire, it's not IoT at all. So forget IoT. And let's say if it is sending it over the cloud, uh, it's really, you don't know basically whether the cloud application is safe or not. So just saying a store scanner is definitely not IoT. And then of course, if you really elaborate on the features, we can decide if it's first an IoT device and then an IoT device. uh yes, Alexa is an example of a smart device. I don't get this question. Okay. Yep, that would definitely be a conversation for another time. See, these are some of the debatable topics that I told you about, right? We can sit endlessly and discuss which of the devices are IoT devices. And I had a nice poll regarding that, but next time. Alrighty, moving on. Uh, right. So your IoT devices are utility centric. Your IoT devices are advanced and robust, right? They should be able to work with different decision making all on their own, right? IoT devices are functionally independent. Again, the light turns on, doesn't turn on, you'll ask it to turn on again, you'll probably fix it. So if it does not turn on, it's not going to affect other machinery of yours or any other work of yours. But again, for an IoT, there's going to be a lot of, if you're, again, IoT can mean a lot of things. It can mean number of devices, or it can be one device with very high stake data, right? So it needs to be able to interact with other devices with uh, a very high accuracy and a good latency. I won't say low latency, right? Scalability. Low scale networks, again, light bulb, one device on the network, big deal. Large scale networks, again, when I say IoT, it means multiple industries, and an IoT system can be 100 devices on a network, or one very sensitive and very high stake device on a network, right? These things can be critically monitored, as in you can monitor them every second, every minute. It really doesn't make a difference. For an IoT, if you're using an RTOS, there'll be systems that need to be very, very precisely timed. In this case, I might even go ahead and give you an example of the airbag in your car, right? If it's not an IoT device, I'm not saying it's an IoT device just yet, but yes, if it's connected and if it's not, you can access it, then yes, it has to be very precisely, uh, automated to come out at the right time, right? All right. So then there is ease of site programming, remote site programming. Your IIoT should be easily updatable. That is something called OTA, right? Or over the air updates. So that's something that's pretty much always a good feature for an device to qualify for an IIoT. Again, your IoT device, it really doesn't matter if it can be programmed OTA or it needs to be programmed physically, right? Okay, again, so IoT, it's convenience. Mostly IoT, if you're actually going to go ahead and install something on such a huge scale, you want some kind of economic growth, right? Resilience, IoT, again, not required. Your light doesn't turn on, big deal. You'll probably just go switch it on. But for your IoT, it needs to be able to work with a lot of faults. It should be able to do a lot of decision making on its own. The use cases are defined in such a way. The programming and the algorithm is so detailed and in depth that the features are so interoperable, basically, that they can be resilient to a lot of faults and work. So let's say you have a network and two devices go down, a good death message and the entire network being able to change their algorithm based on the two devices going down is a really good example of resilience, right? All right. Any questions regarding IoT versus IIoT before we move on? Okay. Again, we're slightly short on time. We're only left with 20 minutes, so I want to give a good 10 minutes to Q&A. So I'm going to cover this part as fast as possible. But if in case we don't, I'll continue in the next session. Yeah. So for example, right, if you connect your light bulb to your Google Assistant or your Alexa, and to your device, they do not need internet to really access. You can always access them over the your local router network, right? uh, Another good example is you using Bluetooth to turn on the light. That is very much IoT, but it's Bluetooth, right? So you really don't need the internet. So absolutely, a local network is definitely an IoT network. Uh, Amazing question. Anyone wants to take a jab at it before I do? I think this is the best example that I can give you, Devang. Uh, it depends on how you're using it, right? It's your entire system, your entire product that qualifies for it to be an IoT or an IoT device or an I. So the best way I like to put it for my workshops that I take is, instead of trying to qualify devices as IoT or IoT, try and look at the system. If you look at and analyze the entire system, it will make more sense whether it's IoT, or whether or not it's IoT, right? That's the answer. It depends on how you're using it and what it's triggering, really. You using an IoT solution, notifying it via your voice assistant, still qualifies for IoT. So again, instead of trying to qualify devices as IoT versus IIoT, try and look at it as a system. Great question, Devang. But did my explanation answer your question? Yes, it is. It is IoT. All right. So no questions regarding IoT versus IoT. More any more questions? And some great questions, I must say. And I've had such great debates with my juniors on these, and I wish I had more time to really indulge in this. But this is a really nice question, and I want you guys to come back with more of this question. So I'll take this up in the later session when we look at protocols, whether or not IoT can be decentralized. So IoT devices can have multiple triggers, right? Like we spoke, sensors, voice. You decide the UI, right? You can control them from the web UI. You can create a Discord bot to control the device. It's completely up to you. There's no better or best solution. It depends on what you're designing the solution for. Which brings us to our next section, which is devices and architectures, right? All right. So if you look up devices and architecture on Google, this is something what should pop up, right? There'll be lots of names, AVR, Extensa. There'll be things like GPIOs. Then there'll be articles telling you, you should consider whether it has an ADC, whether it has a DAC. Then there'll be, articles telling you, your magnitude of the PWM and magnitude of the ADC should be so much. So what are all these terms, right? There's so much to absorb when you're uh, looking at a device, especially if you want it to qualify and think whether or not it can be used as an IoT device, right? Like I said, it'll depend on how you're designing the system, if it's an IoT or an IoT device, right? So these are some of the specs that you'll see if you ever try to differentiate between two devices, right? Now remember, this table, this is a random table that I've picked up to make you understand the amount of specs that can exist in a device when you're selecting it, right? Especially if you're starting from scratch, right? So if you look at the names, right, if you see there's ESP8266 and there's ESP32, both of them are of the same architecture, that is extensor. All right, and in the same architecture there are so many different things that you can see, right? You can see that there's the MCU, which is basically us getting to know the architecture and the core and the other things that you can take out from a data sheet, right? Then there is the network connectivity, and it's standard, IEEE standard. Then there's Bluetooth, uh, whether or not it's available. Then there is tons of random words. I don't know how acquainted you guys are with the hardware specs. So for you, if you're not, there'll be just random words and random letters scattered. All right, so SRAM, flash, GPIO, PWM, SPI, I2C, I2S, UART. So many terms, so many names, right? So how do you really go about selecting a device if there are so many options and so many things available, right? So you basically understand the parameters. So what I will be doing now is I'm going to go through the different parameters available in a device, and when we're writing the script to emulate the device, we'll look into these specs and see where they come in, right? uh, no, the presentation isn't blurry. The table that I picked up is a little blurry. There are so less options available. If I want the license, I want it to be a Creative Commons license, I'm so sorry. When I share the PPT, I think it'll be much more better visibility, right? So let me just go through some of the terms really quickly, right? So I want you to focus on the line that says SPI, I2C, I2S, and UART. Okay, remember, they're all called serial protocols. Okay, they're not necessary for you to select a device in terms of they won't really affect the way your device works, but they will affect the choice of your sensor. So this is important, this parameter, if you're selecting a device, if you know what sensor you want to use. So let's say I know that I want to use MPU6050. That is my sensor, I have to use that. So when I'm looking at a device, I will make sure that it has an I2C, and I will make sure that the I2C is not buggy. What do I mean by that? For example, in this case, if you look at ESP8266 and ESP32, they have a software based I2C and SPI connect. It's not a hardware based SPI connect. So I would prefer a device with a hardware based I2C connection. Why would I still choose ESP32? Why am I still not eliminating it? Because I need a Bluetooth control. Let's say I want it to go over Bluetooth, which is why I will consider ESP32, even though I know that the I2C is probably not the best in the sense of the accuracy. All right, I think this might be better now. The blurriness might have reduced. Okay, awesome. So these are the parameters of choosing the device, right? First comes the architecture. While I guess this would be a contradictory statement and a controversial statement when I say the architecture is kind of not the most important part as much as the last three parameters mentioned, in which case you start with memory and addressing. So what kind of memory do you want? In case if you have a Wi-Fi based network, you want the device to remember the Wi-Fi credentials. So you want there to be some kind of flash or at least an EEPROM to remember the credentials if the device is rebooted. If you have a certain kind of sensor, right? Let's say you have a sensor that gives you 16 bit of data. You need a device that can handle 16 bits of addressing. If you look at microcontrollers, the basic microcontrollers, they start at 8 bit. So you want to make sure that it's a 16 bit controller, right? These are some of the basic things. Then the power consumption. If it's a wearable, right, you cannot have the power being drained every 5 minutes, right? I mean, that's just not done. So power consumption is one of the most important, parameters that I feel isn't talked about enough in the tutorials that exist. Is if it's a wearable, you have to know the power consumption that's happening on your device, right? The current, the voltage it runs at. I have done it as a first year student. I've tried to run a servo motor that needs 5 volts from my Pi, which works at 3 volts, and wondering why it doesn't work. So these are some things that should be considered, that need to be considered when you're looking into your devices. Now I told you that I'm running a servo at 5 volts, so that's another really important aspect to consider. What voltages are your sensors at? You don't want the sensor drawing so much current that it burns your microcontroller, right? Next comes the usage of the power, right? If it's a internet based device and it's going to send data say 5 times a day, you don't want it running all the time. So it should be able to save power when it's not running, right? If you want to save power, it should be able to wake up in time to send the right data. If it sends data late, it really doesn't matter if it's a good device or if it's a nice data if it's late, right? So your wake up time, how much power does it take to go from your sleep to wake up time? That's some of the basic things that you want to consider. Another thing that I completely forgot to mention here is interrupts. How does the device wake up? If the device cannot be woken up in a software way, do you have a hardware trigger every time the data needs to be sent to really wake the device up? Then there is miscellaneous but very important factors to consider. There's networking options. Does the device get connected to Wi-Fi? If not, the module that you're choosing to connect to Wi-Fi, is it really viable? Is that a really viable option? So if you look at Arduino Uno, it can't get connected to the internet like that. You need to attach a Wi-Fi based module, right? Or a Bluetooth module to get it connected to the network. So if your application is simple, you can go for a module and an Arduino Uno. But if it's something more complicated, something that's supposed to run on its own, maybe Uno is not the best option, right? Then there's peripherals. We spoke about I2C, SPI. These are the peripheral options that you want based on the sensors that you're choosing. So if you're sure about the device, you choose the sensors that run on particular serial protocols and not the other way around, right? Then the signal processing, whether the sensor data, if it's ADC, that means if it's giving me an analog data and I want it in digital terms, does your device have ADC? What's the magnitude of the ADC? How do you define a magnitude? Based on the magnitude, you can define the accuracy of the incoming signal, right? That's magnitudes. And then lastly, of course, there's costs. You can't expect people to pay 50K for a wearable device that just gives a good a good heart rate measurement, right? So these are some very important parameters that you need to consider when you're choosing a device. I understand I spoke too fast in the miscellaneous section and there are lots of new terms that I threw at you. So if there's anything you want me to clarify, please go ahead and ask. Alrighty, that's great. So I see no questions, either that or okay, I see no questions. So either you guys understood nothing or everything, and I'm gonna go with everything. Yes, I'll be sharing the PPT for sure. That's a great question, Silicon Bug. So again, you have to check whether or not it will work. That kind of programming works in a device, right? I mean, every device has a different kind of specs, and one of my favorite RTOS is Zephyr RTOS, and that is incredibly difficult to work on. The devices it does not already support. So you need to check what RTOSs support which device. Another really good place to start is platform.io. If you guys haven't looked into it or don't know, I absolutely encourage you guys to go ahead and explore platform.io. It supports NRF chips, which not a lot of RTOSs do. So definitely go and look that up. Thank you. This is really, really reassuring, Umaditri. Thank you so much. All right, great. So I'm going to move on to the next slide. This is just an example of what an entire device looks like. Let's say that. So I've taken up again a random picture to, just to give you an idea of how the periphery really connect with each other. So this is your device. You can see there is a Wi-Fi Bluetooth module. Connected, then there is different, there's SD ram, there is a NOR flash, then there is PWM, and then LED driver, and then you can see that they've also mentioned the low cost LDO. So these things, these small things, they come together to make a really good device, right? And again, MXRT is an ARM based device, so you should definitely look up. ARM is one of the most commonly used uh, terms in IoT. Okay, there's a question, great question. Where can we find RTOS? You can Google it, you'll get a lot of options. But if you really want to understand, I urge you to look into Zephyr RTOS. They have some great documentation. And also look at platform.io. Platform.io lets you connect a lot of different architectures, a lot of different RTOSs, and run it from a single platform through VS Code. So I'm honestly not that comfortable with platform.io myself till now because I've recently started really dabbling with it. But yeah, it's a great thing to for you guys to look into. All right, yeah, I'll be sharing all the links that I mentioned, especially Azure, because I really want you guys to set up Azure on your own before the next session. But if you have any problem, I'll join earlier and we'll make sure that you guys are all on the same page. Embedded systems and RTOS. This is a very superficial overview of embedded systems and RTOS. All right, and let me just cover this quickly and then I'll take any questions you have. Okay. Okay, so what's the difference between an RTOS and a GPOS? How do you qualify an operating system to be a real-time operating system and not a general-purpose operating system? So these are the basic things that make an RTOS an RTOS, right? So let's look at some of my favorite things that really differentiate RTOS from GPOS. Is a preemptive kernel, right? Preemptive kernel means it's you can schedule things and prioritize your tasks, unlike your GPOS, which has response time but it's not really guaranteed. RTOS is usually okay. Before we go on, just because a system uses RTOS does not make it an IoT device. All right, so an RTOS is used to make an embedded system. Now that embedded system can or cannot be part of the IoT depending on the system. Okay, it can be an IoT device but it does not have to always be an IoT device. For example, right, you can definitely code an Arduino Uno with Arduino IDE, have timers, and that would be a really good example of a real-time operating system which is working on timers, which is completely priority based. But that does not make Arduino an IoT device, right? It's running an RTOS, it's an embedded system, but it's not an IoT device. You use RTOS on an IoT device to make it more functional, to make it more fault resilient, right? You can, and I think Silicon Bug spoke about threads. You can use that with an RTOS, but that does not make it an IoT device. You can make an IoT device better with an RTOS, but just because some device uses an RTOS does not make it an IoT device. we will be understanding a good RTOS code that possibly can run on an IoT device, but again, cannot stress upon this enough. Just because a device runs RTOS, it does not make it an IoT device. All right, getting back to RTOS, it's time bound because it works on time. So again, the example I was about to give was a flight emergencies, evacuation system, right? The popping of the airbags, I'm not oxygen masks, right? Or the lights turning on. They're all embedded systems. They're all real-time operating systems, and there's something called hard real-time systems and soft real-time systems. Hard real-time systems are super precise. I mean, to the their magnitude of precision can be like zero point 0.5, like dot on time when it's supposed to do, which is very important in emergency situations, from your car airbag to your flight emergency, landing, takeoff, or those oxygen masks that I spoke about, right? These are very precision times. Now, these are not IoT examples, right? These are examples of really good and hard RTOS systems. All right. Uh, are there any? Okay, I can't see the context of. No, the IoT cannot run both the OSs because most of your embedded systems has RTOS, right? So IoT uses embedded systems to function, and the embedded systems are usually written using an RTOS. They don't necessarily have a real timed operation. That means, because if you're using IoT, you basically want it to be triggered on message command received or sent. So they're not always timed, but yeah, they mostly run in RTOS, right? Thank you so much, Neon, for reminding me. So, uh, is it 6:30 or is it 7 p.m.? Let me just check and tell you. Yep, it's 6:30, and I am so sorry. It's gonna start in 3 minutes. So I'm gonna end this session right away. It is 6:27. I'm so sorry. I remembered it's at 7 p.m. So I'm gonna end this session. We'll continue right from this point at the next session. I'll join a bit early to make sure you guys are on the same page. So I'm gonna have to leave the stream now. Uh, Feel free to connect with me on Discord or any of the other channels that I mentioned. I am always up for a conversation regarding IoT and embedded systems. Again, I'm so sorry about such a weird start and a weird end. I promise the next session will be smoother. And I'm going to end the broadcast now. Thank you so much for joining in, everyone.